of the XCE, all simple seek. Now you remember the first three instructions, the three instructions we saw, which are used for inputting and outputting. Remember, we said that whenever you are going to input data, you have to test the device first, which is going to provide the data. And you remember we said that the device will return a yes or no. If it returns a yes, then it means that it is ready to provide the data. Or if it is in a case of accepting data, then it means that it is ready to accept the data. So unless you get that confirmation, the reading or the writing cannot take place. Okay, and you remember we said that the yes is when we get a less than. When we get less than, that means you can read. But when you get equals, then it means you can't read. The device is not ready. And whenever the device is not ready, then it means you have to go and check again. Okay? And we said that this is done for every character. So if you are going to input like 100 characters, you have to test 100 times or even more, because whenever you test, if it is ready, then you input or you output, then you test again, okay, for the second character and so on until you complete all the characters which you want to read in, all the characters which you want to write. So for every character, you have to read and you have to write. And sorry, you have to test. That is when you read, okay? Now, here is an example of how we can use those instructions. They are saying that this program or the instructions below, we are reading 1 byte of data from a device which is called the F1, and then that character which is read or byte, it is written onto a device which is 05. You remember, we said that these devices have got codes. So there is a code for example, a keyboard. There is a code for a mouse. There is a code for a printer and so on. But each device is identified by a code. So when you look at those instructions which you see on the screen, okay, we have the first device, sorry, the first instruction, it has a label in loop. Then we said that when you are reading a character, you say test device. So you can see that instruction there, test device. And the operand is the device. So test device, I think this means the input device, okay? So we are expecting to get an answer whether the device is ready or not ready. If it is ready, we get less than. If it is not ready, we get equals. So the second instruction there says jump if equal to a label called in loop. Remember, if we get an answer equals, it means that the device is not ready. So it means that we have to go back and we keep ourselves into that loop until we will get an alternative answer. So the first instruction is test device, input device, and then jump if equal to in loop. That means go back in case the device is not ready. But if you get an alternative answer, that means you are getting, let me say, less than, then you can read. The next instruction is read. Then you can read the input device. And you remember we said that when you read one character at a time, and that character which you read, you remember we said is put into the accumulator. The accumulator is 3 bytes, you remember, but when you read, the data you read goes into the rightmost byte, the byte which is on the right. Remember, there are 3 bytes of the accumulator. Okay. Now, if you, after reading, so that byte is in the accumulator, which we have read, you can store character. That means you store what is in the accumulator to a memory location called data. Okay. So that is as far as reading is concerned. Then the next instruction is how we can output. Okay. So again, we want to output a character to an output device. So we can test device, output device. Test device, output device. If it is not ready, we say jump if equal. That means if it is not ready to what we are labeling out loop. So you see where out loop is. That means that you continue with that loop until you get a positive answer. So when you get a positive answer, we are saying that you load the character from that memory device data. That is where we put the character. You can load the character from that memory location data, and then you write to a device, output device. You write to a device, output device, okay? And that is how the declaration or initializations are done. The device is declared by, for example, in dev, you say byte X, and then you put into quotes the code of the input device. Output device, you say byte, and then you put into quotes the code of the output device. X just means that the code is an hexadecimal code, that is hexadecimal. Then since they are characters, we are reserving 1 byte for the data. Okay. Is there a question about that? Okay, so if there is no question, we can continue. But what you have to note about these instructions is that whenever you are going to read a character, you have to test. If the device is not ready, the answer you will get, like we said, is equals. So that means that the device is not ready. So that's why you see that we jump if equals to that label there. And the label just wants to indicate that you are going to keep testing. You are going to keep in your loop. Okay. Someone is asking out loop. This is just a label. Out loop is just a label. Jump if equal. When you say jump if equal, you are jumping to a label. Like when we are writing the loop instructions, you remember yesterday when we were writing, okay? You say jump if equal or jump if less than. We will see jump if greater than, yeah, to a label. That a label is the instruction where you are jumping it to, okay? WD is write device. I think you remember this is what we saw. We said we have 3 instructions for inputting and outputting. Test device, that is TD. RD is read device, and the WD is write device. Okay. Any other question? Okay. Let us go to another example. Now, this is another example, which is about testing and reading. But this time, we are also being shown how we can go to a subroutine. Remember, we said when we are explaining the functions of the register, remember we said that there is the register L. which holds the return address when we return from the subroutine. Now, we know that when you are writing a program, you could find instances when you might be required to call a function, okay? So the way we call a function here, we say jump to subroutine, and then you name the function where you are going. Jump to subroutine. So that is the instruction. We say jump to subroutine is taking you to a function, okay, or another set of instructions. Then when you are done and you want to come back to the main program, you say return from subroutine, okay? So you shouldn't forget that. You say jump to subroutine when you are going to execute or to run a function, and then you say return from subroutine when you come back from the function. And remember, whenever you say jump to subroutine, you remember what happens. We said that the return address where you are going to return it to after the subroutine, that address is stored into register L, okay? Now, here we are assuming in example 6 that maybe we have a program coming from somewhere above, and then you get to an instruction which says jump to subroutine read, okay? So we look for a label which has an instruction which has got a label read, and that is where we resume from. So when you say jump to subroutine read, we are assuming that there are some instructions maybe in there, and then we are going to leave those instructions and come back and go to an instruction which has got that label read. Now you can say read, it is beginning with an instruction load register X with the what is at memory location is 0, and so on. Now this particular program is reading from an input device. There is an input device which is providing data. Come again. Someone is asking something.
So I was requesting that we go through that question, like we read the whole of it, such that when we see these answers, we can be able to compare and contrast the question with the answers, because I saw it was some huge question.
It was somewhat?
It was a lengthy question and it did some comprehension.
Which question are you talking about?
Like before you came to this example 6, I saw there was some question on the previous slide.
Here? That was the previous slide.
As in, first go to the next slide.
This
the one which is having
this one?
The subroutine. Yeah.
You are breaking. I can't hear you well.
Yes, he's talking about this one, this very one, example 6.
Yeah.
Okay,
so I was requesting.
This one is just an explanation.
We read the question.
Okay, okay. But I was trying to explain it, but it doesn't matter. Let us read it. Okay. So this one is saying, it is saying that
okay, so thank you.
It is saying that what we are going to do, okay, with the question is a sample subroutine call and a record the input operations for the simple seek, which means that it is an example of a program where you call a subroutine. Subroutine is just like the function. It is an example where you call a subroutine, okay? And then with the subroutine, the function of the subroutine is to record the input operations. That means you are going to be inputting, and whatever you input is recorded. So that is what the program is going to do. Someone is asking, does that also mean that we should not alter the contents of register L in our subroutine because the address of the current instruction of the program is there, or we can still alter the contents? The address is not there. Here we are just given a label. We are just being given a label. We are going to see how to write the real instructions. But then what you have to notice that when you say jump to subroutine, whichever subroutine you want to go to, automatically the system will pick the return address and it will record that address into register L. You are not the one who is going to put data into register L. It is automatically populated by the instruction. The moment you say jump to subroutine, the system will pick what is in register L, the return address, and it will put it into register L. So you don't. Now someone is asking, what is a simple C? C. Do I have to explain that? Have I been with you? Hello, Harold? Have you been with us for the previous lectures? Otherwise, if you have been with us, we said that the simple instruction computer has got two versions, the simple SIC and the XCE. So we can have the simple SIC instructions where we said that such instructions have got only one format. The operand is always an address. But the XCE, that is a version where we can use registers, where we can use immediate data, and so on. Now, going back to the problem, the example we are going to look at, we are told that this is an example which shows how you call a subroutine. This is an example how to call a subroutine. And then when you call a subroutine, it is going to show us how we input. And whatever we input, we are recording. So we are going to be inputting one character at a time and recording the character which we have input. So the explanation is that the program reads a record which is 100 bytes from an input device into memory. Okay. So from an input device, we record into memory. From an input device, you read a character and the character is loaded in memory. Okay. So if you are going to read 100 characters, then it means you are going to record 100 characters. So the read operation is taken as a function. That is why we said that we will say jump to subroutine, and then we will go to that subroutine which reads. Okay. So the read operation is placed in a subroutine which is called by the main program by using the instruction jump to subroutine. So the instruction jump to subroutine is reading, is the one which reads the 100 bytes from an input device, and then it deposits them into memory. At the end of the subroutine, there is a return from subroutine instruction, which returns the program to the main program. Okay, so the read subroutine has a loop. The read subroutine has a loop because you remember we said that every character you read, you have to test again. So there is that loop there. First, the loop which tests, and then there is a loop which is writing the 100 bytes. So we are writing the 100 bytes into memory in a place called the record. Okay, so that one will show us that when we read, for example, we will write to record 1, record 2, record 3, and so on. Because whatever we read, we want to write it in memory. So when we read, for example, the first character, we write that one in record, comma, 0. Then we read another one, we will write it into record 1. Another one, record 2. Until we get maybe to record 99 or 100, whatever our initializations will be. So that is what the program that we are going to look at does. Is that clear now? Hello? Can we go to the program?
Yes. Yes, we can go, but your network is unstable. Sometimes your volume goes off.
I see, I can see it here also, but when you don't get me, please alert me so that I can go over what I have said again. Okay, so when we look at those instructions, let us look at the program. We are assuming, like we explained, that maybe this is just in the middle of a program. So you get somewhere and you say, jump to subroutine, read. Jump to subroutine, read. That means that you go somewhere in the program and find an instruction which has got a label, read, and then you start executing those instructions from that label. So when you look at the label, we are beginning from load register X with the 0. Okay, so as usual, register X is going to act as a counter. Then we test the input device. If it is not ready, that means jump if equal, because that is when it is not ready. We go back at what we are calling error loop. We go back at what we are calling error loop, and then we test again. So if we get less than, that means the device is ready, then we can read in dev. So we read the input device, okay? And then we store the character we have read, because you remember when we read, the character goes into the accumulator. So now we store what is in the accumulator to record, comma, X. You remember record is a memory location. It is like an array in memory where we are going to be listing the characters we are reading, okay? So we store the character in the record, comma, X. That means if our X is a 0, so that is the first character we store there. Then we test whether we have reached 100, okay? TIX, K100. You remember TIX? That instruction has got 2 functions. First, it tests whether, first it increments X by 1, and then you test whether you have reached that operand. So the operand is K100, which is a word 100. So the operand is just 100, okay? So we increment X and we ask ourselves whether X has reached 100. Now the first time when we increment X is 1. So you compare 1 with 100. That means X is less than 100. So you say jump to subroutine error loop. So that means we go back to the label error loop. And the error loop, like you see, that is when you test again the input device, because it means you are going to input the second character. You test again. If not equal, if equal, you test again. If not equal, then you read the input device. Okay, that means you get the second character, which this time you put in, you store in record 1. Then you increment X. Our X is now a 2, compare X with 100, it is less. We go back and test for the third character. Okay, so those series of instructions are showing you how we read from an input device. I don't know if there is a question there.
Sir, pardon, from jump if less than arrow loop.
We are saying jump if less than, because we previously, the previous instruction is doing two functions, like, TIX, like we said yesterday. It increments register X first, then it tests the contents of register X with what you have in the label. Okay, so you compare. If initially X is a 1, you compare 1 with 100. K 100, we are being told that that is an integer 100. Okay, so the memory location K 100 is holding an integer 100. So if X is a 1, certainly 1 is less than 100. Then you jump if less than to that label, which is arrow loop. That means you go back up there to the label arrow loop, and that label, you test again the input device. If it is ready, you input, you store, then you increment X, you test. If it is still less, you go back and test the device again, read, and then you perform that loop until you get to 100. Is it okay?
Yeah, it's okay.
Okay. Now, if we are going to write this program using the XE, what do you think can we modify to make it easier? Suppose we want to write the XE program. Remember where you can use immediate data instead of going to memory every time. So what can we modify, you think?
Hello. We change the LDX to H0.
Okay.
And then the TIX to H100.
Okay, so that one can work. Okay, but then TIX to 100, that is okay. But again, we remember we said that registers are better, that reading from a register is better than maybe immediate data, because data in a register is available in the CPU. So if you can use a register, it is better. But anyway, let us look at this one. The jump to subroutine read still remains. Now we are looking at the XE version. Okay, then we load register X with the immediate 0. We can also load register T with the immediate 100. Remember, we have either register T or register S, which are working registers. We can use any. So the other instructions remain. But when you come to compare, you can compare now what is in register X with what is in register T. Because from above, we have put 100 into register C. So this time you say TIXR. TIXR, that means the increment register X and compare register X with register T. So if it is less, then you go back and read the next character. And then you just here have to initialize the input device. And of course, you initialize the 100 bytes. You reserve storage for 100 for record, which is 100 bytes. Okay. Is it fine? Anybody having a question? Because those are enough examples. We are now going to look at the real programs. Remember XCE. Sorry, remember SimpleSeq, the simple instructional computer, is being used to introduce us to the system's software, the assemblers, the compilers, the loaders, the link, like we are going to see. Now we know how this works. We know its registers, we know its instructions. So we can now start the real business. Any questions so far there? So if it is okay, then I think that is the last thing about this chapter 2, which is the simplified instructional computer. Let us look at something else. Okay, you see my screen?
Yes, sir.
Okay, so that is where we are going. I request a lot of attention because some people usually find this stuff a bit hard, whereas it is very easy if someone paid attention. So this is assemblers, okay? Now, what did we say an assembler was? Remember when you were starting? Someone who can't hear? But I hope other people can hear me, I hope. Don't you hear me? I hope you can hear me. Because my system is at its maximum. Can someone remember what an assembler does? Can someone remember what an assembler does?
It converts assembly code to binary code.
Okay, I'm sorry about that, but here I am reading your answers, and I think all of you have got an idea. Assemblers mainly translate assembler language instructions like the ones we have been writing. We have been writing assembler language instructions, and they are converted to machine language. Because you remember when we were discussing the machine language, we said that the machine does not understand the high level. It doesn't understand even the assembler, but it understands only a machine. But remember, we said that the difference between the high level and assembler is that for every assembler language instruction, you can write an equivalent machine language instruction. And the reverse is also true. For every machine language instruction, there is an equivalent assembler language instruction. So assemblers translate assembler language to machine. That means a language of zeros and ones. So someone says it is a program that takes basic computer instructions and converts them into a pattern of bits that the computer's processor can use to perform its basic operations. So many words, but just meaning simple thing. These basic computer instructions are assembler language instructions, not a high level. But otherwise, it is a compiler which converts a high level. But the assemblers, they are the ones who assemblers translate assembler language to machine language. Okay. It provides a mapping between instructions written in assembler code to their equivalent language which accepts people like it and translate them into machine language. Okay. But it accepts assembler language. So the basic functions of an assembler is to accept as the input assembler language program, and then it produces its machine language equivalent. Okay, so an assembler accepts or it inputs assembler language, and then it outputs or it produces machine language equivalent. So we are also adding there something else, that it produces its machine language equivalent along with the information for the loader. You know, like we are going to see, when you write a program, the first thing that is done is to have that program translated into machine language. Okay. Now, after translating it to machine language, then it is loaded in memory, because the memory takes only zeros and ones. Memory does not take in the high-level language or assembler language. So when you are loading a program in memory, the program has to be a machine language program. So when the program is going to be loaded in memory, maybe some instructions have to be given, like from which memory location the program is going to be loaded, because in memory, there is a lot of stuff at any particular time in memory. See? So after converting, excuse me, after converting the program to machine language, then the assembler will also generate information which will enable the loader to load that program in memory. We are going to see another software called a loader, which loads the machine language into memory. So the basic function of an assembler is to accept as the input assembler language program and produce its machine language equivalent along with the information for the loader. So that is basically what we are saying, that if you have an assembler language program, you pass it to through an assembler, and then you will get machine language. And also you get what we call a listing. A listing, these are the instructions which are needed by the loader. So you get machine language instructions and then the program listing, which is needed by the loader. And then after the program is loaded, like we see later on, it is maybe passed through a linker and then it is executed. So that is what you have to note as far as the instructions or the functions of the assembler is concerned. An assembler is a software, systems is software which converts assembler language to machine language, and it also produces information required by the loader to load that program. Now we are going to start explaining an assembler using a program. We start by using an example of a program which we are going to see, or it is somewhere here which you can see, but let us first explain what it does. So that program which is going to be used as an example, it has a main program. It has a main program. And then that main program will call two subroutines. So after, when the program is running, it will get to a time when it will call a subroutine. So one subroutine is called the read record, which we are abbreviating as the RDREC. Okay. And then another one is called the write record, which we abbreviate as WRREC. So those are two functions which are called from the main program. The main program is running, it gets to a certain point and it calls a function read record. So after reading a record, then of course you will find a jump to a return from subroutine instruction. So it returns to the main program, then it continues the main program, and then it will get to another instruction, jump to subroutine write record. Okay, so it also goes and executes write record, and then it returns to the main program. So the main routine records the input, records from an input device, which is called the F1, and it copies them to an output device, which has got a code 05. So what the RDREC does is to read a record. So it is like the previous example, which we saw, where we are reading a record and putting the characters which we have read, we put them into memory. So this one is also going to be reading. Okay, so the function RDREC, it is reading a record from an input device, and when it reads it, it copies it into memory. Then WRREC, which is write record, it picks the characters which were read, which were deposited in memory, and it outputs them or writes them to an output device, which is code, which has got a code 05. Now subroutine RDREC reads a record, like I have said, into a buffer. A buffer is some storage in memory. So it reads a record, like you remember, one character at a time, which means that is going to be a loop. Whichever character is read, that one is put into a buffer in memory. Then a subroutine write record will write the record which is in the buffer, and it will be outputting it to an output device. One character is transferred at a time, that is what we said. Now, when you come to the end of the record, okay, you will read what we call a null character, which is represented by a 0. So remember, we are saying that we are reading from an input device, and whatever we read goes into a buffer. Okay, now when we read from a buffer, then we write to an output device. So the indicator that we have read the whole record is when you read that null character 00, that will mean that you have reached the end of that record. Okay. Now, if the record you are reading is more than those 4096 characters, then we stop. So on the record accepts only 4096 characters. And when we reach the end of the file is indicated by a 0 length record. So if you read a record which has got 0 length, then it means that you have reached the end of the file. Okay. And then the end of the file is detected. When the end of the file is detected, what you write to the output device are characters EOF, which mean end of file. Now, this is just a basic explanation which you need to understand if you are going to understand the program, but you will understand it better as we look at the instructions themselves. You remember, our main concern is to know how to translate an assembler language program into a machine language program. That is the main issue. Okay, now the program we are talking about is that one. That is the program we are talking about. Like you can see, there is it is beginning with a directive start. You will realize that most of our programs start with a directive start. And when you get to the end of the program, usually there is a directive end. Okay. Now, the name of the program is usually the first label there. So in this program is called the copy. That is the name of this program. So that is where you write it, copy. That is the name of the program. Then there is a label, start. What you see there, 1000, like we are going to explain, that is the memory location where that program is loaded in memory. So we begin from, it is loaded from main location 1000. Okay. So we are going to call a subroutine. We are going to call a subroutine read the record, because we said that is what the program does. But you remember we said that before a subroutine is, you go to execute a subroutine, you store the return address into register L. So here they are saying STL return address. So return address is stored into register L. Then you go to a subroutine called the RDREC. Now RDREC is on the next page. So this is the program RDREC. When you look at it, this is the subroutine or the function which is reading from an input device. So like you can see, it is very similar to the last example we said. Load register X with the 0, then you load the accumulator with the 0, test input device. If equal, you test again. Okay. If it is ready, you input. Now there we are saying compare with the 0 because we are going to do it. There is a limit on what we read. Yeah? So we compare with the 0. Okay. So if you remember 0 is the null character, we said that whenever you read a null character, it means that you have come to the end of the program. Sorry, to the end of the record. Okay. Then you store what you have read into a buffer X. You test whether you have reached the end, and then you go back. So that one is the routine read the record. And after reading the record, there are some more instructions you read, like LD length, compare 0, jump if equal to end of file. Then you find another subroutine which says jump to subroutine, write record. Remember, this is the one which writes record is from memory, the buffer, and it writes the characters onto an output device. So that is jump to subroutine or direct and so on. So this one basically is the program. It might take you time to actually understand what it does, but it is not a big problem because like you can see all the instructions you see here, we have already met them. There is no new instruction. All the instructions have been met before, okay? So that is the main program, which is called the copy. This is the subroutine, which is called the read record. And then that is the subroutine, which is called the write record, okay? So when you are free during your time of revision, I want you to go through these programs and continue understanding exactly what is happening. But for us, we are now going to concentrate on how to translate these instructions to machine language. Okay. Now, that program is rewritten now. We are going to, the program is going to be rewritten again when it is showing the object code, that means the machine code for every statement. And assuming that we begin, like we said, that it is loaded from address 1000. Now that is the same program. That is the main program. Then this is the subroutine RDREC. And then that is the subroutine WRREC. Okay. So it is just the main program, the program we have just seen. But we have added there 2 new columns. You can ignore this column, which is blank, but there is the first column. This column is a column for addresses. So when this program gets loaded in memory, because you remember we are saying that after translating it, it is going to be loaded in memory. Memory takes only machine language instructions. So we have to know the address where it is going to be loaded from, okay? Now remember, we assumed that it is going to be loaded from a memory location which we called 1000. So this first column here is showing addresses where each instruction will be found in memory. Each instruction will be found at that address in memory when it is translated to machine language. And then the last column here is showing the machine code. You remember we said that every assembler language instruction, there is an equivalent machine language instruction. For every assembler language instruction, there is an equivalent machine language instruction. So the instruction STL or return address, its machine language is that. The instruction jump to subroutine RDREC, that is its machine language. The instruction load the accumulator from length, that is its machine language equivalent, and so on until you get to the bottom where you have these directives like a reserve word, reserve byte, because those ones are just reserving storage. They are not instructions. Remember, we said that directives are not translated to machine language. Which table are you talking about? This is a program. This is not a table. So which table are you talking about? Alan? I said this is a program. If it is a program and you are going to write another program, then you are not going to use this. This is just a program which is being translated. And I'm saying we are going to show you how to translate. So I don't know what you are, I mean, what is bothering you? Okay. Okay. Maybe Just a moment. Let me remove this screen and then I will load another one. Just a moment. Okay, now if you can look at my screen here, we saw this screen when we were trying to explain the instructions, okay? Now, each of these assembly language instructions has got a code. Something wrong, you can hear some noise. Someone, can you please mute your phone, your microphone? I can hear some voices from the background. Okay, so I was saying that we saw that every instruction has got its machine language code. So the instruction to add, if you are adding it to memory, like we said, we have the cases like add num, add marker, when the operand is a memory location. This one is a what? Its code is 108. Add the float, if we are adding using a floating point accumulator, the code is 58. Add the registers, that is the code. So this table will always be given, because you can't cram the what? You can't cram these codes. What you need is to know that this particular instruction, this is its machine language code, and so on. So as we explain, as I explain, we will keep on looking at this table. We will keep on looking at this table as we go along or explaining, okay? That's why I asked you to get at least familiarized with this table so that you can always be able to interpret it, okay? Like this one, add the registers, R1, R2. We said it is a format 2 instruction. The opcode for adding registers is 90, okay? This one adds the contents of register R2 to contents of register R1, and the answer is put into R2. And this one is only on the XE format. It is not only the simple seq, because the simple seq does not use registers, okay? So, and so on. So please, as we continue explaining, we will be also looking at this table here, okay? So let us go back to our other program. Okay, so this is where we were. So I was saying that every instruction has got its machine language equivalent, okay? Now with this one is a simple seq program. You remember a simple seq, all instructions have got only one format. This is something I want you to note very carefully. If it is a simple seq, all instructions have got one format. We have the opcode, you remember it is the first, then the opcode, then from the opcode, of course, there is that bit number 9, which just tells us the type of addressing mode you are using, whether index or direct, and then the address. So every instruction for the simple seq, we should know the opcode and the address. So that gives us the what? That gives us the machine language instruction. Now let us look at the first instruction. Maybe before we do that, remember we said that the machine language instructions for the simple seq, does anybody remember how many bytes it consumes? A machine language instruction for the simple seq, how many bytes does it have? Hello? Are you there? Okay, it has got 3 bytes. You remember, if I can remind you, the format is we have an opcode which is 8 bits. Okay. Then we have that bit which we call the X. It is 1 bit which tells us about the addressing mode. And then we have the address, which is what? Which is 15 bits. So when you add the 8 plus 1 plus 15, I think we get 24 bits. 24 bits, that is 3 bytes. So if we are going to be using a simple seq, every instruction is 3 bytes, okay? So if you begin with the memory location 1000, and that is why you put this instruction STL or return address, it means the next instruction will be at 1003. Then the next instruction will be at 1006, because all of these instructions are simple seq instructions and they are all 3 bytes. So that is why you see that the interval here is 333. Is that okay? Because every instruction is consuming 3 bytes. Okay. Now, you remember the format. We are saying that the format is in such a way that you begin with the opcode, then the address. Now, if we want to translate the instruction STL or return address, okay. Now, does anybody have the opcodes? Let us look at the opcode for STL. Does someone have the opcodes so that you can tell me what is the opcode for STL? Story. What is in register L to return address? Does anybody have the other table for opcodes? Okay. If nobody does, then
The opcode for STL is 14.
Come again.
The opcode for STL, I think it is 14.
Oh, very good. Very good. I was going to show you. For those of you, the opcode for STL, you look for STL. STL store what is in register L. The opcode is 104. Does everybody see that one? It is 104. Is it okay? You have seen it? Oh, maybe you haven't seen it. The opcode for STL is 104. Everybody, I hope, sees that. Is that okay? Can I hear something from you? Because we are going to keep on moving between these slides, because we need the opcodes to translate to machine language. So it is 104. Okay, so let us go back to the other program. Okay, so there we are. So if the opcode is 104, so that is the opcode. So what we need is the address of return address. Okay, so we have to find out where return address is, the address where it is going to be found, the label return address. Okay, now if you look at the program, I think you find the return address down here at a memory location, which is 1033. Do you see that one? At 1033, that is where you find, that is the address where you find return address. Okay. So if we are going to translate the instruction STL or return address, we need the opcode for STL, and then we need the address where return address is located. So STL is 104. That is what we said. And then the return address is at 1033. Is that right? So you can see that the machine language instruction for that instruction, STL or return address, is 141033. That is the machine language, because we need only the opcode and the address. The opcode is 104. The address of the operand is at 1033. Therefore, the machine language for that instruction is 141033. Is it okay?
Yes.
Any question about that? Please, I want us to go slowly because I don't want it to leave anybody behind. This is still some simple stuff which can get a bit complicated later. But if we understand it from the beginning, then it will become very easy. Okay, let us look at the second instruction. Does anybody have that table to tell us the opcode for jump to subroutine?
The opcode for jump to subroutine is 48.
Is 40.
48.
Yes, very good. Now let us translate this instruction, jump to subroutine RDREC. Now jump to subroutine, the opcode we know is 48. Okay. So what we want is the address where RDREC is. Okay. Now RDREC is on the second program. RDREC, if you can see this function RDREC, this one is loaded from memory location 2039. Okay, so that is the address where you find the RDREC. Okay, therefore the machine language instruction for this instruction, jump to subroutine RDREC, is 482039. 48 is the opcode for jump to subroutine. 2039 is the address where RDREC is. So that the machine language instruction becomes 482039. Okay. Okay, let us look at the next one, LODA length. I think you remember LODA. LODA, when you were doing the other calculations, we said LODA is 00. Does everybody remember that? But even if you don't remember, you can look at the table. The table will always be given. So the opcode for LODA is what? 00. So what we need is to find the address of length. Now, when you look at the program, the address of length is at 1036. Therefore, the machine language instruction for that particular instruction LDL length is 001036. Okay. Okay, sorry for that. Have you now understood how we translate the simple C program from assembler language to machine language?
Yes, sir.
Yeah, you just need the opcode and then the address of the operand. That's all you need, okay? So we are saying that the translation of an assembler language program to object code is that code which has got zeros and ones, is as follows. You convert the mnemonic. That means you remember what we mean by a mnemonic. That is the abbreviation for the instruction. So you convert the mnemonic operation code to their machine language equivalent. Like for example, you translate STL, it is 104, and then you convert the operand to their equivalent address. So if the operand is a return address, you get its equivalent address, which is 1033. Then you build the instruction in the correct format. We are going to see the correct format is you have to know the format of the instruction, opcode, then bit number 9, and then you do it, and then the address. Then you convert the data constants into their internal machine representations. For example, you need to translate EOF to 45, 4F, 46. Let me show you, let us see that one. Okay, like when you look at this program here, at this address 102A, EOF, they are saying byte characters EOF. Now, since these characters are loaded into memory, since we are loading these characters into memory, and into memory we have got only zeros and ones, you remember we said that in memory, every character is represented by its ASCII code, okay? So that's why you see that the machine language for EOF is 45, 4F, and 46, which is the ASCII code for character E is 45, the ASCII character for O, the ASCII code for character O is 4F, and the ASCII code for character F is 46. So these ones they have also to be translated into machine language. Okay.
Pardon for me, sir. My network was off and on.
Okay, we said that when you have these instructions here, we have seen how to translate the instructions. You just need the opcode and the address. But when you get to the data also has to be converted to the format which is acceptable in memory. For example, when we talk about characters EOF, I said that the characters, you remember we said that characters are represented by their ASCII codes in memory. So you should know the ASCII code for character E, that is a 45. The ASCII code for character O is 4F, and the ASCII code for character F is 46. Okay, so that is like the machine language instruction or the machine language data for that particular code. Then the word 3 since we said that every word is 3 bytes, so we don't talk word 3, you have to put it also into 3 bytes. Word 0, you have to put it into 3 bytes. Yeah? So that is how those ones are translated. Yeah. These people, you have asking very much. Will your skill code is be given? If need be, if need be, they will be given. But at least you know now E or F. E is the 4-5, okay? O is the 4F, and the F is the 4-6. At least you know that, okay? So that is what we are saying. If I can repeat, we are saying that to convert an assembly language program for the simple SIC to machine language, you have you convert the mnemonic to its machine language equivalent like STL. You read, you find that it is 104. Then you convert this operand from a symbol to the machine address, because in the program it is given as a symbol. So you find the address for return address, it is at 1033. Then you build the instruction in the corrective format. The format is the opcode, the address, okay? And then the data, you find also its machine language equivalent.
Everyone was very okay. Everyone was attentive.
The data, you find it equivalent machine language equivalent, like those characters E or F, they are 4-5, 4F, 4-6. And then the last thing is to write the objective program and the assembly listing. You write the objective program, that means you write all those instructions in their machine language equivalent, and then the assembly listing, which we are going to see, okay? Okay, now, I hope that is okay, unless someone has a question before we continue. That is very important for the simple SIC. Okay, now we go ahead and it said translation of the addresses. Okay, now, one thing that you have to realize here is that everything is easy if we have the table which has got the opcodes. Okay, like that table where we read that STL is 104, jump to subroutine is 48, LDA is 00, and then we also have these addresses. Everything becomes, I think, easy. But the problem which can make it maybe a bit hard is that these addresses are not always given. The addresses are not always given. So they will always give you the beginning address. Like in this case, they will just give you 1000, okay? And then they will ask you to translate that program to machine language. So it means that you have to generate the addresses yourself. You have to generate the addresses yourself. You can't translate before you know the addresses, because every instruction will need an address, okay? So if you are going to translate an assembly language instruction to machine code, you need to know the addresses, okay? Now, I'm saying that the addresses are not always given, so you need to generate them yourselves. So what usually happens is that before you even think about translating, you need to generate the addresses first. I think that is logical in order to get to know where each operand, at which address every operand is to be found, okay? So we usually say that the assembler makes 2 passes when it is going to translate an assembler language program to machine language. It makes 2 passes. That means it goes through the program 2 times. The first time is to generate the addresses first, okay? So from the top, you go on allocating addresses to every instruction until you get to the bottom. Is that right? Then you can go back at the second time. That is when you do the what? The actual translation. Is that okay?
Pardon, sir. Not getting so.
I said that usually translation becomes easy, or it is always easy, so long as you have the addresses and so long as you have got the what? You have got the table which has got the opcodes. I'm saying that table is always given, but the addresses, you are the one to do it, to generate them. So they will give you only the beginning address. And then from the beginning address, you will go on finding out where each label, the address of each label, because there are these labels which will always be referring to as the operands. Like when they say LDA length, we have to find the address of length. When they say jump to subroutine RDREC, we have to know the address of where RDREC is. Is that right? So that is what we mean by when we say that the assembler will usually make 2 passes. That means it usually goes through the program 2 times. The first time is to allocate addresses to every symbol, every label. You have to know the address of every label. Is that right? And then you also need the table which has got the operation codes. That one is given. So when you have the addresses and you also have the table which has the opcodes, then you can easily translate the program. Is that okay? Hello?
Yes, it's okay. Question is, how do you generate them? Because I'm seeing from 100, from whatever, from 100, you go to 1003, like that. So in a bit, so 33.
I think I explained that. Maybe you didn't hear me. I said, if you remember the format of a machine language instruction for the simple SIC, we have got only one format, which is 24 bits. We have 8 bits for the opcode, 1 bit for that addressing mode, and 15 bits for the address, a total of 24 bits. 24 bits, those are 3 bytes. So it means that every instruction will take 3 bytes in memory. So if the first instruction is to be found at memory location 1000, the next one should be at 1003. Don't you think so?
Yes, sir.
And so on. Every instruction is 3 bytes for the simple SIC. Okay. And the 3 bytes,
Okay.
those are 24 bits. If we write in hexadecimal, how many hexadecimal digits do we need? How many hexadecimal digits do we need to write an instruction?
4.
Are you sure? We have 24 bits. Each digit, each hexadecimal digit is 4 bits. So how many digits do we need? How many hexadecimal digits do we need to write 24 bits? I think there are 6. Is that right? Okay. So that's why you see in this column that every instruction is 6 digits. Every instruction is 6 digits. These are hexadecimal digits. Okay, every instruction is 3 bytes, which mean 6 hexadecimal digits. Okay, so when we come back here, we are saying that translation of addresses to their equivalent codes is complicated because when the addresses are unknown, and because we don't know the addresses at the beginning, most assemblers will make 2 passes over the program. Okay, so what is done in the first pass? The first pass is to go through the program. That is what we mean by scanning the program. You go through the program, finding where every label is. Okay, and then you assign the address to every label. You assign an address to every label, and then those addresses are saved. You put them into a table. Okay, then you come to process those other data areas like we saw when we processed like the EOF. That one we put 45, 4F, 46, and so on. So all of that is done during the first pass. Now during the second pass, that is when we do the what? The real assembling. That means that is when we do the real translating, because we know the addresses and we know the opcodes. Okay. Okay. So that is when we generate the data values, like we said, those define byte, define word. So where they say reserve word, of course you have to leave 3 bytes because the word is 3 bytes. If they say, for example, reserve 2 words, it means you have to give space for 6 bytes and so on. So that is what we mean by processing the directives. And then you write the objective program and the listing onto some output device. Okay. Now the tables, these are the names of the table. That table which has got the operation codes, we call it the operation code table. The operation code table. That table where you read that STL is 14, jump to subroutine is 48, LDA is 00. We call that table the operation code table. So that is the table we use to look up the mnemonics and translate them into their machine language equivalent. So the table has mnemonics, which we translate to machine language. Okay. Then when we get the addresses, there is what we call the symbol table, which we abbreviate as a SymTab. So this is a table which you generate when you assign addresses to all the labels. So this one is generated during pass 1. During pass 1, you remember, we assign addresses to all the labels. Now every label is put into a table. Okay, so we have a symbol table which has got the name of the symbol and then the address of that symbol, the name and the address. So this one is called the symbol table. It is used to store addresses which are assigned to labels. Okay, it has the name and then the address for each symbol. Okay, then we have a counter. This one is not a table, but it is a counter. Because in the previous example, we said that we are beginning with 1,000. Okay, so that is the initial value. So this counter is initialized to that value 1,000. So that whenever you go from one instruction to another, you go incrementing by 3 by 3. So when you find a label that value in the counter is what you enter into the what? Into the symbol table. And then you go on like that, like that. So we have a counter which helps you to count, or in other words, to determine the addresses of the symbols. So we usually ask those ones what their functions are: the operation code table, or op tab, the symbol table, and then the location counter. Okay. So during pass 1, we will need.
Network was open.
Come again.
That slide.
So what is not clear here?
From SYM tab, from the symbol table.
Okay. You remember we said that every symbol needs an address. Every symbol needs an address because, sorry, a machine language address. Because when we say, for example, STL, return address, we need to know the address of return address. When I say LDA length, I need to know the machine language, the actual value of address length. Okay, so every symbol needs an actual address. So the symbol table, which we call the SIM tab, which we abbreviate as a SIM tab, is the table where every symbol is put together with its address. Every symbol and its address are put into the symbol table. Then to generate those addresses, we need to count, because we are just given only one value, the starting value, which is given. Like in our case, they said was 1,000. So that is the only value which is given. So we call it a location. We have a location counter. That means it is a counter which we go on incrementing. Wherever we move from one instruction to another, we go on incrementing it. So like in this case, since all the instructions are 3 bytes, we go on incrementing by 3, by 3, by 3. So when you find a label, the value of the counter is the address of that label. So you enter it into the symbol table. Okay. So that when you come to translate now to machine language, you have got 2 tables. You have the table which has got the operation codes, which is provided. And then you also have a table which has got the addresses, the symbols, the addresses of the symbols. Is that okay?
Yes.
Okay. So during pass 1, op tab is used also to look up and validate operation codes in the source program. Okay. So this one is also done in, it is also done in pass 1. Pass 1, the main function, like I said, is to generate addresses. But then there is also something else which is done during pass 1. This is to validate the operation codes, to make sure that you wrote the right code. For example, you can write LDA and maybe you forget A and you write only LD. So that one is not known. So validating whether the code which you have written is the actual codes for assembler language, that one is also done during pass 1 before the real translation is made. Okay, so that's what we are saying, that in pass 1, the operation code table is used to validate the codes which have been written in assembler language. Okay, then in pass 2, we use the operation code table for the translation to machine language. Okay. In the pass 1, like we said, all the labels are entered into the symbol table as you encounter them, and then they are assigned the addresses. Then in the second pass, we just read the symbol table. That means that is where we find the labels and their corresponding addresses. Okay. Now, I will beg that we stop here today and you internalize that, because the next thing will need a lot of time. Translate, writing the machine language, the object listing, that will take us some time. So I request you to make sure that you read this. I'm going to send it to the class rep, this slide here of chapter 3, the assemblers. Any question? So if there is no question, then we adjourn the class until next Wednesday. Is it Wednesday? Hopefully. Until Wednesday at 10. Have a nice week and weekend. Okay.